Okay. All right, sometimes we'll go over homework first, sometimes we'll kind of go over homework second, so it kind of varies. All right, this time we're going to kind of go over the homework first. So pull your homework out. All right. Let's see if we've got some questions about something. So just tell me kind of what page and what problem it is causing you some trouble. Will?
Whatever it says on the domain and range.
We're going to go over that today. So you can do the reading, but I think when I look over it today, it'll make it a little bit better for you.
Yeah,
Was that it?
Oh,
Okay.
that was two of them. I was like,
Oh, I know. Anything besides domain and range. Are we okay on doing stuff like finding slope, writing equations of lines, those kind of things, okay? All right. And then on the functional notation, is everybody okay on doing things? Do you have like number 9 where you sticking numbers in? Okay. Is everybody okay on something like, well, I don't think I didn't give y'all, maybe I did. Did I give y'all 27 yet?
Yes.
Okay. 27 bothers some people. Okay, so I do want to make sure and clarify something. 27 is something called a piecewise function. Okay? Because when you graph it in 2 pieces. So we're going to talk about that in just a second. Okay? But do you understand, like, you've kind of got 2 graphs. You've got an f of x was either 2x plus 1 or a 2x plus 2. Is that right? Okay. Now, how did you know when to use which piece? The top one you used when x was less than 0, and this one you used when x was what, greater than or equal to 0? So what that means is if you're plugging in a negative number, you should have been plugging in up here. If you're plugging in 0 or a positive number, you should have been substituting what? Right there. Is everybody okay? So everything's going great until you got, some of y'all got confused probably when you got to t squared plus 1. All right, how do I know whether to put t squared plus 1 in the top piece? Do I put it in the top piece, the bottom piece, or both? Well, how do you know I put it in the bottom?
Because you can't put anything in there.
No matter, if it's a t squared plus 1, what if t was 0? If you put 0 in there, what's going to come out of this whole thing? 1. What if you put in like a 1? 1 squared is 1 plus 1, what's going to come out? 2. What if you put in like a negative 2? When you square that negative, it's still going to be what kind of number? Positive. And when you add a positive to a positive, it's going to be what? Positive. Are negative numbers ever going to fall out of this? No. So that's how you know, no matter what, t squared plus 1 is never going to be negative. So that's why you should have plugged it in the bottom of them. Does that make sense to everybody? Okay, so if we're going to do domain, we'll do domain and range first. Other than domain and range, does anybody have a question about anything on your homework that you want to ask?
what's supposed to be the answer to 53?
Let's see what 53 is. Which page are we on?
16.
All right, 16. Put back over. All right, 16. And we're doing 53. All right, 53, what, did it tell us to write the equation of the line? Okay, and then it said we had to do it in what kind of form? In general form? Okay, what 2 things do you need to write the equation of any line? A slope and a what? And a point. All right, so I need a slope and I need a point. Now, they gave me plenty of points. They told me the x-intercept and the y-intercept. Now, if the x-intercept is 2, 0 and the y-intercept is 0, 3, I can use either one of those points. All right, so if I want one of 2, 0 or something, okay? But I'm missing the slope. Well, how do you find slope? Isn't that the difference in the y's over the what? Difference in the x's? Okay, so my other point was 0, 3. This point's 2, 0. So let one pair be x1, y1, and the other pair be x2, what? Y2. So my slope's going to be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So what does it end up being? A negative what? 3/2? Is that right? All right. So anytime you want to write the equation of a line, use that point slope line. So y minus y sub 1 equals m times x minus x. Now remember what we said last time, one pair of x's and y's has a subscript and one doesn't. So the pair with the subscript are the ones that you go grab your point. okay? So y minus, now I don't care if you grab this point or you what? Or that point. I already put that point, so I'm gonna grab it. So that'd be y minus what, 0 equals 2 times x minus what? 2. What's y minus 0? Y. Now, if I don't tell you what form to leave it, you could leave it like that. But they said they wanted it in general form, right? So general form is like a number in front of x plus a number in front of y equals another number, okay? So y would be what, 2x minus 4? Are we okay? So if I want to leave it in general form, what would my general form be? A number in front of x, so to speak, plus what? A number in front of y would equal another what? Number. So if they tell you they want it in a certain form, then you got to leave it what? In that form. Is everybody with me? Now, if they don't tell you what form to leave it in, you can leave it what? In any form that you want to. Oh, except what's my mistake? Oh, what's my slope? It's not 2, what is it? Now, if I make a mistake, tell me. That's what happens when I'm trying to look over there and look over here. All right, so that's going to be a negative 3/2. So that's going to be a negative what? 3/2 x. What's a negative 3/2 times a negative 2 going to get me? Plus 3? Okay. And so the same kind of thing. I'm going to have a negative 3/2 x, and then it'd be minus y would equal what? 3? Now, there's 2 ways. Some people do general form this way. This is really the most common, but I've seen your author do it like this sometimes. Does that make sense? So really either one of those is general form. Some people most mathematicians are going to put it equal to c, but if you'd rather put the whole thing equal to 0, that would be general form too. So,
Do
question.
you prefer equal to C?
Doesn't matter. I'll take either way. I'll take either way. It's just usually out of habit, I'll do it the top way. But that's just habit. Either way is good. Okay. Are we all right? All right, then let's kind of go do domain and range. Okay. Let's go do domain and range. Now, first of all, let's define them. Remember how we said that functions were a set of ordered pairs? All right. The domain's the set of all the first coordinates of those pairs. The set of all the first coordinates of the ordered pairs. In other words, you would think of it as your x's, most of it, okay? But all points aren't x, y, okay? Your range is the set of all the second coordinates in your ordered pairs. In other words, you would think of that as a set of your y's. So we talked about functions. Domains are the numbers coming in, and ranges are the numbers coming out. Okay? So a lot of times what they want to know, remember we said a function is, when one thing comes in, how many things can come out? 1. So you can't have one thing come in and like 2 or 22 come out, and you can't have one thing come in and nothing come out. So a lot of times we talked about functions are a lot of times an infinite number of points. So I couldn't literally list every individual point, all right, or every individual first coordinate. So a lot of times when they say, what's the domain, they want to know what's legit. So what can you put in the function that will send something back out? Now, what we're going to do is, in Cal 1, there's really only 2 times that you're going to have trouble spots. Let's call them trouble spots. All right. Now, let me show you what I'm talking about when I say trouble spots. Okay. There's a number that if you substitute in here, the world ends and it's your fault. Okay, what's that number? 6. So anything but 6 is fine to use. So they would say the domain is all real numbers except what? 6. But now, what if instead it was like this? What if that was your function? And I said, what's the domain? You can't tell at a glance quite as easily as you could before, right? So what's a way to figure that out, the ones that are going to cause you trouble? Yeah, in other words, a minute ago when you said 6, because in your head you looked to see what would make that bottom equal to 0. Well, this one's a little harder to look at, but I can certainly go to the side and figure out what makes the bottom 0. Now, are those numbers that make the bottom 0, is that my domain? No, my domain's everything what? But those. So, I'm going to say your first trouble spot are rational functions. All right, I'm just going to say rational functions, rational expressions, however you want to phrase it. Now, a rational is when you've got a polynomial on top of another polynomial. What you think of is when you've got a fraction with a variable in it. Okay? So what I want you to do first then is I want you to set the denominator equal to 0. Okay, because that's what you told me to do. And then I want you to solve that. But your answer, when you solve it, that's not your answer, correct? What's your domain? Everything what? But that. So your actual domain is going to be all real numbers except those solutions. Remember, solutions are the numbers that make something true. All right, so you copy that down, and then we'll go do kind of an example of that. All right. So there's my rational function, my rational expression. Now, is the denominator the top part or the bottom part? What's the denominator? The bottom. So I go over here to the side, and it says set it equal to what? 0. Now, we talked about this the other day. How do I solve a quadratic equation? What do? Factor it. Now, I don't care if you factor it by trial and error, tic-tac-toe, quadratic formula, just factor the thing. Okay? Whatever makes sense to you. Now, I tend to do trial and error. The only way to get x squared is an x times a what? An x, if I'm going to be using, integer coefficients. Now, just a quick review. When this constant has a minus in front of it, what does that tell me about the operators in these parentheses? They're one of each. Now, if there's a plus in front of that constant, it tells me that the operators match. They're either both plus or both minus, and they would match that middle. Okay? So because I've got one of each, one of these is a plus and one's a minus. Then in my head or on paper, I'm thinking of all the factors of 6. What can you multiply together to get you 6? 3 and 2, what else? 1 and 6. Now, because I'm going to end up subtracting because the signs are going to be opposite on those middle terms, then I'm trying to find a pair that subtract to give me a -1. Now, which pair differ by 1? The 3 and the 2. And I need the bigger one to be behind the negative because I need them to be combined and give a negative. So it's going to be a minus what? 3 and a plus 2. Now, take 15 seconds to multiply it back up either on paper or in your head, because sometimes I'll have a calculus student that'll get something wrong on a test because they didn't just take the 3 seconds to double check themselves. So x times x is indeed x squared. I'm going to get a minus 3x plus what? 2x. And that is a minus what? X. And then positive 2 minus 3 is a minus 6. Now, when you've got two numbers that multiply together to give you 0, we know that one of those two numbers must have been what? 0. So either x plus 2 is 0 or what? X minus 3 is 0. So what's the solution of this first one? What do you add to 2 to get 0? -2. All right. Or here, what do you add to get rid of that -3? All right, so I get two answers, a -2 or 3. Now, is that my domain? No. So what's my, now capital D is domain, so what's my domain? All real numbers except what? -2 and or 3. Now, you can write it in words. Now, they're never going to write it in words in the back of the book because they pay by the keystroke. You know, it's by the page that when they pay to get it printed. So they're more than likely going to do like this. And that's funny looking R stands for real numbers. And they'll put X not equal to what? That's called algebraic notation. All right. I've also seen them put it in interval notation. Interval notation looks like this. Now, let's review. Parentheses, does that mean include or don't include? Don't. What means included? A bracket. Now, you never put a parenthesis around an infinity. An infinity is not a number. Infinity is a concept. Infinity just means something continues without a bound. So here, we're saying start at -2, but don't include what? -2. And this says go to the left, what? Forever. Well, you can't include forever because where was that? You see what I'm saying? That's why there's a parenthesis. Then this one says, okay, start back at -2, but again, don't what? Don't include it. So you see that this just skips over -2. And then it says go straight from -2 to 3 and get all those, but don't include what? 3. Then this one says, okay, start at 3, but again, don't include what? 3 and go to the right what? So the back of the book could legitimately have any of those. Now, your book tends to really like interval notation. And that's great. I'm just kind of lazy. So on this one, that takes so freaking long, I probably just put that. But, you know, we all speak, you know, the language, so English is always. Okay, so that doesn't mean you're not smart if you use words. Okay, so feel free to do either way. So anytime you got a rational expression, now I don't mean like this. Everybody with me? In other words, 2 is never going to equal 0, so there'd never be anything to throw out. I'm talking about when you got a polynomial over another polynomial. Just take that denominator to the side and set it equal to 0. Now, sometimes you don't get anything. See, if I were to set that equal to 0, wouldn't I have x squared plus 6 is 0? Which would say x squared is a what? -6. Are you ever going to square something and get a negative number with real numbers? So what does that mean? What do you have to throw out? Nothing. So this domain would be all real what? All real numbers. So just because you have one doesn't necessarily mean you have to throw something out. But that's what you do when you got a fraction, when you got a polynomial over another polynomial. Is that clicking? Okay, let me show you your second trouble spot. All right. Your second trouble spot. Sometimes roots are problematic. Now, let me ask you this. Square root of a -8. Am I going to get a real number answer to that? No. What about the cube root of a -8? Am I going to get a real number answer to that? Yeah. What's the cube root of a -8? -2. So it matters what this number is. Now, when there's not one showing what's it understood to be. 2. So I don't get in trouble when I have odd root index numbers. I get in trouble sometimes when I have what? Even. So when I say even powered roots, does that communicate? So I'm talking about this index number. If I've got an even index number, then I may be in a little bit of trouble. Okay? So make sure we're clear about this. So what if I had something like, all right, and I said, what's the domain? Now, you can start throwing numbers in there But guessing and checking is gonna be problematic because it's got an infinite number of answers. All right? So what do you think would be the best thing to do this time if I've got an even powered root to figure it out?
Greater than or equal to 0.
All right, now, with this junk under the root, the fancy word for the stuff under the root is a radicand. That's the stuff under the root. So you're telling me to set that radicand what?
Greater than or equal.
Greater than or equal to 0. Okay. All right, I think that's a great idea. All right, so I'm going to go over here to the side then, and I'm going to set, what's my radicand over here?
That's just 3.
All right, 2x plus 3. I'm going to set it greater than or equal to 0. Okay, you solve that on your paper and see what you get. All right, you get 2x is equal to negative 3. So what's x greater than or equal to? Negative 3 over 2. Now let's review some negative numbers for a second. You can, if you add a negative or subtract a negative from an inequality, nothing weird happens. Okay, if you have to divide both sides or multiply both sides by a negative inequality, what do you have to do to the inequality? You got to flip it, you got to reverse it. Okay, so here I'm good either way because I was dividing by 2, but just for review. Some people forget to flip. Now, this. Now before, I threw that away. But what is this time? Is this my domain or is my domain everything but that?
That is your domain.
That is my what? My domain. Okay, so tell me what my steps are going to be on this. I set the radicand greater equal to 0 and I solve it. Now this time, that answer is the domain. So as long as you pick number, if you pick a negative 1.5 or anything bigger, you're going to be fine. Give me a number that's bigger than negative 3/2 or negative 1.5. 1, 0, 100. What about negative 1? Is negative 1 bigger or smaller than a negative 3/2? Bigger. Anything to the right? Everybody with me? So even if I put it, you don't tell me x can't be negative. X can be negative in this one. This whole thing can't be negative. Is everybody with me? And see, if I were to put a negative 1 in there, 2 times a negative 1 is a negative 2. What's a negative 2 plus 3 though? 1. And the square root of 1, don't you get an answer? So these are close enough to be dangerous. Okay, so let's make sure we're clear. If I've got a rational function, if I've got a rational, I take the bottom off and I set it what? Equal to 0. But if I've got an even powered root, I take what's under the root and set it greater than or equal to 0. So one time it's equal, one time it's what? Greater than equal. Okay, so that's close enough to be dangerous. The other thing that's close enough to be dangerous is on the rational expression, when I finished, got the answer, that's what I've discarded. But over here with this radicand, when I get the answer, that's what I keep. Okay, so make sure you kind of get them straight. When do I throw something away and when do I keep it? Now, with Cal 1, with the problems that are in your book, that's really your only 2 trouble spots that they're going to have you run into. So if it's neither one of those things, your domain's just all real numbers. So it doesn't have to be pretty. Here's what I mean by pretty. I mean, that's a pretty ugly equation. But the domain is what? Are real numbers. In other words, all I want to know is when do you get an answer? Now you say, well, I thought you said you couldn't have fractions. I said I couldn't have fractions where the variables are. Everybody with me? And see, that variable's not anything to do with the fraction. I thought I couldn't have anything where with even powered roots. Well, that's when the variables are under the roots. Okay. So if the domain bothered you, then is that better? So kind of go back and look at those. All right, we okay? All right, now here's the other thing I want to talk about. Let's go back to that idea of a piecewise function for a second. Okay. That we talked about on your homework. I gave you something like this. Here's your piecewise function. F of x is 2x plus 1 if x is greater than or equal to 0. I mean greater than or equal to 1. And f of x is x squared if x is less than 1. So we never substitute a number in both. We look at what we're plugging in or substituting in. If we substitute a number in that's smaller than 1, we only plug it in this piece. If the number we're plugging in is exactly 1, we substitute in that top piece. Everybody okay? If it's bigger than 1, it goes in what? The top piece. Now, if I told you to graph it, would you be okay? All right, let's make sure we're clear. Do you understand that your one picture is really a combination of two pictures? One time, let's kind of color code it a second. All right. One time, now in f of x, the same thing as y. So one time you're graphing y equals 2x plus 1. Now what's that going to graph for you? A line. All right, another time you're graphing y equals x squared. Now what's that going to graph? Parabola. All right. So I'm going to come over here and graph it. Now I was going to go back old school and do t-tables. Okay. Give me a number to substitute for x that's legit. Can I plug in a 0 right here? Because I want to.
Yeah.
All right. Why can't I plug a 0 in here?
Okay.
Because this says you can only plug in numbers there that are what? 1 or what? Or bigger. Is everybody with me? So I can't plug, I can plug a 0 in, but it's not legitimate. I don't have permission to do that. So what can I plug in? I can plug in a what? A 1. All right. What's 2 times 1 plus 1 more is going to give me? 3. Give me another number that's legit I can plug in. 2. Okay. Well, 2 times 2 is 4. What's 4 plus 1? 5. Now, how many can I plug in? Many as I want. But you already told me what's this gonna be a picture of what? Of a line, or at least part of a line. So how many points are necessary? 2. Now the teacher sometimes will make you do 3 just in case you get one wrong. Is everybody with me? But I mean that's sufficient. So I've got the point 1, 3. Then I've got the point 2, 5. Now, does everybody understand why I didn't go to the left? Because you told me I couldn't plug in 0, right? So I only get the part of the line when x is 1 or bigger. Is everybody with me? Now, let's go graph this piece. Now, what numbers am I supposed to use here? Numbers that are smaller than what? 1. So give me a number that's legit that I can use. 0, okay. What's 0 squared? 0. All right, so 0, 0. Okay, give me another number that's legit. Negative 1. All right, what's a negative 1 squared? 1. So negative 1, 1. Give me another one. Negative 2. Okay, what else? When you square negative 2, what do you get? 4. Now again, you knew what shape. What's this supposed to be? Parabola. So how many points? I don't know. I might need 3. You might need 23. Now, when I finish, there's going to be something wrong with it. I want you to tell me what's wrong with it. That's not exactly correct. Why? What's wrong with it? I'm missing some points. This is supposed to be all the x values smaller than 1. What about a half? Is a half smaller than 1?
Yes.
But see, I don't have anything there. Is everybody with me? So here's what I'm going to have to do. I'm going to have to fudge. Here's what I mean by that. Do I really have permission to put a 1 in here?
No.
No, because it said it had to be what? Smaller than 1. But do you know the very first number that's smaller than 1? See, I don't. If you say a half, I'm going to say, what about 1 over 17? If you say 0.9, I'm going to say, what about 0.9999387? Do you see what I'm saying? So what I'm going to have to do is fudge a little bit. Now, this is just Gans notation. You can do it any way you want to. I usually put a star there. That reminds me, I'm not really supposed to plug that number in. Is everybody with me? When I put 1 in, isn't 1 squared 1? This tells me where to back the graph up to. Now, if I put a half in there, a half comes out to be a half squared is a fourth. Is everybody with me? So a 1/2 would have been a fourth. 2/3 would have been 4/9. Is everybody with me? When I draw this point I'm not really supposed to have, I'm going to draw it as an open hole. So that's the point 1, 1. That tells me what to back the graph up to. Because I don't know the very first number that's smaller or bigger than a single value. So when this splits, it legitimately goes in one graph and it doesn't go in the other piece. Is everybody with me? So the piece you're not really supposed to substitute into, substitute in, but when you graph that point, make sure you graph it as not a closed hole, but a what? An open hole. Then you got all of your x values covered. Now, is this really a function? Well, what's your glancing test when you look at the graph to see if something's a function? Vertical line test. So sure enough, wouldn't it just clip one place, one place, one place, one place? Now, what happens right here at 1? Now, it hits this, but what's that open hole mean? There's nothing there, so it still just hits what? Once. Is everybody with me? So this really is a function, but it's called a piecewise function. Now, just because it's a piecewise function, sometimes the pieces connect and sometimes they don't. Now, in this one, they don't connect, do they? Everybody okay? But I can change them so that they do if I want to. Now, what do I mean by that? Suppose, suppose that had been 2x minus 1 instead of 2x plus 1. Do we understand that this parabola would still be there? But this line would be different, wouldn't it? If it were 2x minus 1, what would happen when I plugged in a 1?
1.
I'd get 1, wouldn't I? When I plugged in a 2, wouldn't I get what? 3. So when I went to do 1, 1, does everybody understand? And I did 2, 3, wouldn't my closed hole get filled in right there? So just because it's a piecewise function doesn't mean they're always going to be disconnected. Sometimes they're connected and sometimes what? They're not. It varies from problem to problem. So I do expect you to be able to find me domain of any functions. I do expect you to be able to graph me a piecewise function. I do expect you to be able to know where to plug the numbers in if I give you a value. So anybody got a question about anything so far that we've gone over? Does that make sense? Are we okay? All right, let's talk about composition of functions for a second. All right, because that's over here as well. All right. All right, suppose I have different functions. All right. Suppose this is my first one. It's going to take whatever comes in and it's going to add 3. Suppose I've got a different function. Let's call it something different. Let's call it g. Maybe it takes what's coming in and squares it. So they do two different things. So common sense, if I said F at 1, do I plug 1 in just the top one, just the bottom one, or both? Because it says put 1 in the what? In F. Is everybody okay? So I'd have 1 plus 3 and get 4. If I said, okay, what's G at -3? That means only put -3 in which one? In G. So what happens when you square that? You're going to get what? 9. But if they do this, do we know what to do? Now, that's called a composition of functions. Now, let me tell you what a composition of functions does, if you don't remember. It's sort of like if I work at Nissan over in Canton and building cars, does one person make the whole car? What? No. So my job might be put the front doors on the car. Is everybody with me? And then that gets passed to the next people, put the back doors on. So does it make sense that what my team ends with, the next team would what? Start with. That's what composition of functions does. Okay? So it moves from one function, and when it's finished, that goes into the next function. It's like train cars. Okay? Now, here's what I've discovered. Most people are better off rewriting this. This says F composed with G at 2. If I were you, I'd write it like this. Do you see that F is first both places and G is second? But here's why this notation is better for most people. You're accustomed to seeing what we call nested groupings, like parentheses inside of other parentheses, right? Do you work outside in or inside out? So this says put 2 in which one first? G. Then what do you do with that answer? That answer is going to go in what? Yeah. And if you read it this way, I'm afraid you'll put 2 in F first. Is everybody with me? So if you write it like this, you're less likely to make that mistake. Now I'm going to show you 2 ways of doing it. I'm going to do it what I call pictorially first and then algebraically. Depends on what kind of learner you are. So what is 2 going to go into first? F or G? G. All right. So G is going to square stuff. Now what happens after it gets through with G? Then it goes into which one? F. Okay? So if you think better in pictures, do it pictorially. Now what is it telling me to put in? Put 2 in what? In G. So 2 is going to come in here. Now what's going to happen? It's going to take that 2 and do what? Square it. So what falls out of this? 4. Now, so do we understand that when you put 2 in G, what fell out? 4, right? Where does the 4 go into? The 4 goes into what? F. Now, what's F going to do to it? Whatever falls in it does what? It adds what?
3.
It adds 3. So what's going to fall out at the very end? 7. Now, you don't have to do it pictorially. I mean, this says put 2 into G, right? So you could literally go up here and put 2 into G. Well, 2 squared is indeed what? 4. So either way, this G of 2 gets replaced by what? 4, whether you do it algebraically or whether you do it pictorially. Now, what does the 4 go into? The 4 goes into F. Okay. 4 plus 3 is indeed what? 7. So I don't care whether you do it pictorially or whether you do it algebraically. Now, go do this for me. What does it mean for something to be commutative?
Same backwards and forwards.
Same answer, different what? Order. Addition's commutative. 2 plus 3 and 3 plus 2, what? Same answer. Is subtraction commutative? No, not in my checkbook. I wish it was, but what? It's not. So I want to know if composition's commutative. So you did F composed with G at 2. Why don't you go do G composed with F at 2? and see if you get the same answer. So on your paperwork, this one for me for practice. And again, whichever way you want to work it, you can work it algebraically, you can work it pictorially, but I would have to see your work and give you credit. God bless you. Now, do we understand that means G at F at 2? See the order? G's first, F is second. But what is the 2 going into first this time? F. So if 2 goes into F, what's going to fall out of here? 5. Is everybody okay? So what's that 5 then going to go into? G. So when you put a 5 into G, what's it going to do to it? It's going to square. So what comes out? 25. Did you get the same answer? So composition of functions is not what? Commutative. It matters which one happens first. Right? Just like in the real world, some things are commutative. If I had on a shirt that buttoned, and I started at the bottom and I buttoned all the way to the top and said, okay, look at it, versus I started at the top and buttoned all the way to the bottom and said, look, or skipped around. Would the end result be the same or different? It'd be what? The same. But putting on your socks and shoes is commutative. If you put on your socks first and then your shoes and look at it, that's going to be different than put your shoes on for some strange reason and then try to put on your what? Your socks. We're going to be a little worried about you. Okay? So not the same. So some things in the real world are commutative and some things in the real world are not commutative. Okay. Now the other thing it talks about in your book is if you look on page 23, it talks about transformations of graphs. Okay? Now, I'm not going to take time to go through all that. That's like what you learn in algebra. Let's just make sure we're clear about something. They're what they call some parent graphs. Okay? And it's helpful if you know the general shape without that grapher, because on that third test, you're not going to have what? The grapher. Okay? But can't you always make t-tables like we did a minute ago? Now, you know what y equals x squared graphs. What is y equals x squared graph? Parabola. Okay? So if you've got a parabola, y equals x squared, what's your vertex? 0, 0. So what happens when you take a parabola or a parent graph and you just like add 3 to it? What's it do to that original graph? It just shifts it up. If it was -3, it would shift it what? Down. That's what happens when you just tack numbers on at the end. Now, if you did this is the one that's a little weird. Now notice, let's put +3 since I put +3 a minute ago. I didn't tack the +3 on at the end. It went with the variables. Everybody with me? Now this is the one that to me is not intuitive. This one is intuitive. Up and what? Down. Now here, this is when it shifts either what? Left or what? And it's going to be backwards from what you're probably expecting. What's this +2 going to do to that original parabola? Shift it what? To the left. And the -3 would shift it what? To the right. And again, that's just good if you don't have your grapher to kind of know. So they remind you about those shifts. All right, what happens if they change the sign? Like y equals x squared, that parabola's going to turn up. But if instead I do y equals a -x squared, what's that going to do? The parabola's going to flip it what? Down. So things can flip, and that's kind of the coefficients start flipping some stuff. So they just remind you down at the bottom where it says basic types of transformations, it just reminds you about those transformations. What do cubics look like? You know what cubics look like? They're basically S-curves. Everybody with me? Now, the same things do on trig. I went ahead and put up that trig review. Okay? So there's a video out, there's a link to a YouTube video that I made out on Moodle. It's a trig review that you can go look at so if you want to double check some things. Now, but even without your graphers, I expect you to know the general shape of sine and cosine. Like, use your hands. What do sine and cosine look like? They're away. All right, now get the particulars of that, it's not a problem if you make yourself a little tea table. All right, tangents and cotangents, what do those look like? They're S-curves, so one goes this way and the other goes that way. Is everybody with me? Okay, so now, do you know what secants and cosecants look like without your graph? All right, they flip on you. Now, we'll talk about that next time. I'm gonna do a little bit of trig in class, not much, but a little bit next time. Because 1,000 years ago, I didn't have a graphing calculator, so I had to learn to graph them by hand, okay? But they're super simple to graph by hand. I'll show you. So unless it's something weird, I just don't grab that graph for a whole lot, which is kind of nice because a lot of times on standardized tests, you don't have them. You know, MCAT, LSAT, you know what I'm saying? Like, they expect you to just kind of know some things and then, you know, use some thinking skills and figure some stuff out. So we'll kind of look over that a little bit. All right, so that kind of takes care of this section 1.3. Now, there's some definitions on page 26 that you already know. You just don't know that you know them. Okay? They talk about functions being even or odd. So sometimes they're going to ask you, is this function even, odd, or neither? Now, an even function is symmetric to the y-axis. An even function symmetric to the y-axis. And we already went over symmetry. So remind me, how do you see if something's symmetric to the y-axis? What do I do? Replace what? Somebody said replace what? X with a negative X. If I get the same thing, then I have symmetry. If I don't get the same thing, what? I don't. All right, an odd function is symmetric to the origin. But remind me how we checked origin symmetry before. What did we replace then? Both of them, right? So you replace X with a negative X. And you replace Y with a negative Y. You got to do both. So replace X with a negative X, replace Y with a negative Y. Now, think about it. Y equals X squared. That graph we were talking about a second ago. Isn't it symmetric to the Y-axis? If you fold along that Y-axis, won't this fit right on top of that? So instead of saying it's symmetric to the y-axis, you might just call it a what? An even function. That's just two ways of saying the same thing. All right, origin symmetry. The example I think we used one day was y equals x cubed was that S-curve. Remember, that's where you fold twice. You fold on x and y. So instead of saying this graph's symmetric to the origin, you might just say this is an odd function. That's just two ways of saying the same thing. Now, which symmetry doesn't get a cool name? Well, why don't we have a cool kind of function name for x-axis symmetry? Wouldn't be a function. See, if you had something like x equals y squared looks like that. Is everybody with me? That's got x-axis symmetry, but if it's got x-axis symmetry, it's not a what? Well, you can't be a cool function if you're not a function. Okay, so it doesn't get a cool name. Okay, so on your test, I might ask you, I might say, is this function symmetric to the origin? Or I might say, is this function odd? That's just two ways I might phrase the same question. I might say, is this function symmetric to the y-axis? Or I might say, is this function even? Now, almost every test is going to say, prove your answer. In other words, you can't just go, yes, with supreme confidence. Okay, or no. Okay, so you have to kind of back up what you're saying. All right, so that's just something you already knew, you didn't know you knew. Okay, all right, now, that kind of takes care of this section 1-3. Now, 1-4 is trig. Now, what I told you on the video, have any of you watched it yet? Okay, now, let me kind of tell you on the video. If you look on the video, you may not need to watch the video, that's optional. That's just in case you need kind of a trig review. You're gonna have to be able to do trig in here. And you can ask anybody that's ever had me, I love trig. So there's gonna be trig on every calculus test. Okay? So it's not like just hold your breath and it'll go away and not go anywhere. Okay. Because you're gonna have trig in Cal 1, Cal 2, Cal 3, and Cal 4. All right, so we might as well like get it fixed down here, kind of my philosophy. Now, with that said, I didn't teach you high school. So I don't know how you learned it. Some of you got all the answers off of the unit circle. Now, you are very welcome to get all your answers off of the unit circle. I just ain't got time to memorize the unit circle. Okay? So if you got it memorized, use that. But in your head, you're just seeing the unit circle and plucking the numbers off. Is everybody with me? But what you can't do is have your little unit circle on a piece of paper beside you on the test, which some of you did in high school. Okay? So if you're going to use the unit circle, then you got to memorize the unit circle. And it's really not that hard to memorize. I mean, I'll come show you a shortcut to sort of memorizing it, but I just ain't got time for that. So what I do is use right triangles. And the advantage is, this is section 1-4, in section 1-6, everybody got to use triangles. Okay? Because the unit circle ain't gonna help you. So again, I think there's an advantage to using triangles. And the reason I did it is because back in 8th grade, I had to memorize 2 special triangles, a 30-60-90 and a 45-45-90. So I still had to memorize something, but when I got to high school, I'd already memorized that. So I wasn't gonna waste brain space and memorize something extra, you know what I'm saying? Let's just say I'm efficient, so I'll say I'm lazy, okay? So I just used what I already knew, and it really worked out to my advantage. But you are gonna have to, and it tells you in the video, there's some things that you're gonna have to know. Like if you open your textbook up, like we talked about last time, that very first day, if I open this book up, this very first flap is a tear out. I wouldn't tear it, but it's a formula sheet. Well, there's calculus on the first, but on the back side, there's trig. Now, you don't have to know all of this trig to be finding Cal 1. But there's some of it you are gonna have to know. So what you are gonna have to know is you're going to know basically in words what the trig functions are. Like, if I'm using words like adjacent, opposite, and hypotenuse, what's cosine? Adjacent over hypotenuse. What's secant? Hypotenuse over, everybody with me? So make sure you go back and review them in words. Now the other thing you'll have to do is you have to use them in terms of x, y's, and r's. Now, here's what it's also going to tell you real quick in that review. I'm not going to take time to do the whole thing because it's on the video. But I do want to make sure we're clear about something. Here's the only part of the unit circle that I really bothered, and really I had to memorize it. The unit circle means you got a circle whose center is the origin and the radius is 1. Well, common sense would tell a person, if the center is the origin, the radius is 1, what's it force that point to be? 1, 0. What would it force that point to be?
0, 1.
0, 1. What's it going to force this one to be? Negative 1, 0, and what? That's Gann's view of the unit circle. Done. Okay? Now, common sense also tells you this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant what? 4. Well, again, I don't memorize things when I can figure them out in 3 seconds. It's a waste of brain space. So if I want to get in quadrant 1, I go right or left? Right, and then what? Up. So if you go right, that means the first number had to be positive. Up means the second number had to be what? Positive. If I want to get in quadrant 2, I don't go right, I go what? Left, and then I go what? Up. If I want to get in quadrant 3, I go what? Left, and then what? Down. And to get in quadrant 4, I go what? Right, and then what? See, again, I don't memorize, I just use common sense. So cosine of an angle is defined as x over the radius. Well, what's the radius on the unit circle? 1. So that means on the unit circle, the cosine is the same thing as the x coordinate. That's why they like that unit circle. You just have to look at the x coordinate. Similarly, sine is y over the radius, but what's the radius? 1. So on the unit circle, the sine's just your y coordinate. Now, what's tangent in terms of sine and cosine? It's sine over cosine, so that forces tangent to be what? Y over x. Now, you got reciprocals of these. What's the reciprocal of cosine? Secant. So instead of it being x, it's going to be what? 1 over your x. You see my point? Now, so here's the lovely part. The lovely part for me then is I already had these memorized. All right. If I do a 30, 60, 90, the side across from 30 is a 1, the side across from 60 is a square root of 3, hypotenuse is 2. Okay? On a 45, 45, 90, because these angles match, the legs match. 1, 1, hypotenuse is a square root of 2. So I memorized that when I was 12. So I'm done. So when you ask me something like, what's the cotangent of 30 degrees, in my mind or on paper, I just sketch that real quick. Now remind me what cotangent is in words like adjacent, opposite, and hypotenuse. What's cotangent? Adjacent over opposite, okay? Here's 30 degrees. What's adjacent? Square root of 3. What's hypotenuse? Excuse me, the opposite's what? 1. And the square root of 3 over 1 is just square root of 3. All right, if I want the sine of 45 degrees, what's sine in words? Opposite over hypotenuse. So what's my opposite? 1. What's my hypotenuse? 2. Now, I don't know who taught you high school. I'm not going to rationalize that. I don't have time. Now, if I need to rationalize it, what? I know how to do that. But here's the reason again, I got time for that. To rationalize that, you multiply the top and bottom by this root on the bottom. Everybody with me? So if you multiply the top by the square root of 2 and the bottom by the square root of 2, you indeed get the square root of 2 over what? 2. Now let me tell you why they used to rationalize 1,000 years ago. Really like this. In your mind, that is 1,000. All right, get your calculator out with me for just a second. Now, I need you to understand that even around 1970, which I know to you seems like 150 million years ago. Are you with me? But that's really literally like 50 years ago. Is everybody with me? Those machines in your hand didn't exist. So you had to do all this junk by hand. Now, give me a decimal approximation for the square root of 2. 1 point what? 414. I'm going back now. First of all, this is before my time, but apparently it took a whole lot of work to get this because you didn't have a machine you could just punch it. So there was a whole algorithm you had to do to figure this out. Well, then you could work 2 long division problems. This says 1 divided by that number. This one says that number divided by 2. Which long division problem you want to work?
The second one.
That's why they rationalized it. You doing that anymore by hand? So I got time. Everybody with me? Now, sometimes if I'm going to be adding a bunch of them, I'm sometimes more comfortable having the denominator to be 2 than what? the square root of 2. So again, there's sometimes I am going to rationalize it to make my life better, but just because I don't have time. So on a test, I know math, so I don't care whether you put 1 over the square root of 2 or what. Square root of 2 just make your life happy. Okay? Now, so I do expect you to be able to get the correct answers exact. Do not ever give me a decimal approximation. Ever. Unless I specifically say on number 15, you may give me a decimal approximation. Which will only happen like once on the third test. And here's the reason. Part of my job is to get you ready for the real world. Okay? So there's different reasons why you need calculus in your majors. Some of you are actually going to use calculus. Engineers actually use calculus. Most doctors do not. Now some do, but most don't. So why in the world is calculus, why do we have it in pre-med? What do you think? Critical thinking, which one did you think? See, when somebody comes and plops down in your office and says, you know, I have a headache and my throat's a little, so, you know what I'm saying? That's going to fit 95 diseases. Medicine's not an exact science. So you're going to have to be able to sift through and in your head come up with, okay, what's the most likely thing? Maybe they got a sinus infection. Give them a $4 bottle of amoxicillin, everybody with me? And send them up, you know what I'm saying? Now, if that cures it, they're fine. If it doesn't, they come back. Well, you have to kind of start over with the problem solving. But you can't order a PET scan for everybody. Could be a brain tumor. But not likely. Is everybody with me? So it's the same thing in calculus. I need you to think, and I need you to understand what you got when you got it. Well, if I work for NASA, nobody builds the space station by themselves. Everybody with me? You know, you don't have to build it, you don't do anything by yourself. Everything's done on teams. So you problem solve on teams. So this team does a little piece and then hands their findings to the next team. Is everybody with me? So if it comes out to be the square root of 2, I'm not going to hand the next team 1.414 because I don't know what they're going to do with that number. And if in their calculations they have to multiply the number I give them by 100,000, what happens to that little bit of error that I gave? It just blew up. So when the hammer comes down and somebody gets fired, it's not going to be me. It's like I handed you the square root of 2. You took it upon yourself to round off. That is your problem. Now, in the real world, this is exactly what happens. This was probably now 20 years ago. They were going to send a probe to Mars. They were going to land the little rover. It's going to like drive around Mars, snap some pictures. Everybody with me? Okay. Billions of dollars. We blast off. It goes to Mars. It probably lands on the very edge of a crater, falls in and freezes. Our bad. Sorry, we talk to taxpayers. You know. Here's what they found out. It didn't land where it's supposed to land. It was supposed to land on the edge of a crater. Okay? So why did it land in the wrong spot? This is what happened. One team's working in the English system. Feet, inches. They just hand their number to team 2, who's working in the metric system. See, a measurement's a number and a unit. Is everybody with me? It's lazy to say that the length is 2. I mean, 2 feet, 2 miles, 2 minutes, what are you talking about? But somebody, you see what I'm saying? So it's a big deal. I mean, that's $1 billion down the drain for a small, no, we're not going to do that. Okay, so into the mini sermon. Now, so I do expect you to be able to do this. Now, they're never going to use degrees in this book. They only use radians. So you can do scratch work in degrees, but you got to, they're going to give you radians, you got to give them back radians. So they're never going to say, what's the sine of 45? They're going to say, what's the sine of pi over 4? So you got to remember that pi radians is the same thing as what? 180 degrees. So when on your review sheet, if I ask you something like, you know, what's the secant of 3 pi over 4? You're probably going to need to change that to 135 degrees in order to find out what your reference angle is.
No, I was just
Okay.
like counting.
Does that make, yeah, no, it's not doing the same thing. Does that make sense? Because the trick thing, whether the answer is positive or negative comes from the quadrant. The number comes from these triangles. So if I wanted the secant of 3 pi over 4, you could say 3 times 180 divided by 4 with your calculator, and you're going to get 135 degrees. So what quadrant are you in? Quadrant what? 2. Now, what is secant the reciprocal of? Cosine. Did cosine depend on x or y? X. In quadrant 2, look at me. What? In quadrant 2, x is what? Negative. So this answer is going to be what? Negative. But now instead, what if it had said cosecant of 3 pi over 4? Well, cosecant is the reciprocal of sine, and sine depends on y. And what is y in quadrant 2? It is positive. What if it had said tangent? Well, tangent is y over x. So if you take a positive divided by a negative, it's going to end up being what? Negative. Everybody with me? So the SIGN comes strictly from the quadrants. Do it first so you don't forget. Then the number is the reference angle. It's going to remind you on the video, if you're in quadrant 2, your reference angle is 180 degrees minus your given angle. So 180 degrees minus this given angle is going to be 45. So now I go find the secant really of what? 45. Now here's the other sweet piece that surely somebody showed you at some point. Here's the other sweet thing about when they give you in radians. There's your reference angle. 45. If you had 5 pi over 6, your reference angle is going to be 30. If you had 5 pi over 3, your reference angle is going to be 60. So the number answer comes from your reference angle and your triangle. The SIGN comes from the quadrant. So play with that a little bit. Now, remember I told you that I learned 1,000 years ago to graph them by hand. Okay, let me show you why that's not hard at all. Remember the unit circle that I learned or figured out? Only had 4 points on it. 1, 0, what? 0, 1, negative 1, what? 0 and 0, what? Negative 1. Okay. So here's what I did. Pi over 2, isn't that 90 degrees? Pi is 180, right? 3 pi over 2 is 270, and 2 pi is 360. Negative pi over 2 would be negative 90, correct? Negative pi would be like negative 180, negative 270, and negative 360. We good? All right, all I need is a unit circle. All right, if I'm doing the unit circle, all right, suppose I want to graph y equals sine 0. What's the sign of 0? Is sine the same thing as your y coordinate? So what's the sign of 0? 0. What if you're at 90? 1. The sign is your y coordinate, which is 1. So at 90, it goes up to 1. What about at 180 or 3 or pi? I'm all the way over here inside your y coordinate. So what is it? 0. At 3 pi over 2 at 270, what's your y coordinate? Negative 1. If I go back to 2 pi to 360, now I'm back to y being what? 0. Now, when you're going this way, it's positive. What happens when you go clockwise? Isn't that negative angles? So what if you're at negative 90? What's your y coordinate? Negative 1. So if I'm at negative 90, I'm at negative 1. If I go to negative 180, what's my y coordinate? 0. If I go to negative 270, my y coordinate is 1. And then if I go back, I get a 0. Everybody with me? Cosine is just the same graph, should go from 0, 0. You understand it's the same thing, just what? Shifting. Now, what about tangent? Well, I do the same thing with tangent. I just go over there, every time I get undefined, I get an asymptote. But here's how I did secant 1,000 years ago. Aren't you going to be in trouble when the x's are 0? Because it's secant 1 over x. So everywhere that I have an x value of 0, that's where I'm going to end up with an asymptote. Okay? So, let's see. I'd be in trouble here, wouldn't I? Where else am I going to have a 0? Isn't it right here? Everybody okay? In other words, wherever x is 0, so it's 0 here and what? Here, so that's going to be at what? Okay, so I'm going to be at 0, so at pi over 2 and so forth. So all I got to do then is start playing with these things, and then I just flip them. Because that's what reciprocal does. It does what to the graph? It just what? Flips it. So if you draw cosine and get your asymptote, then you just flip. And then you've got secant. If you draw sine, same kind of thing, because this one was what, sine x? So that's where I'm going to get zeros on my y values. So those go to 0, then I just flip them, and I can get cosecant and secant. All right? Now, where's your homework always going to be? On Moodle. Now, we'll check something though. You're going to have a homework assignment basically on functions. But what else is due on Wednesday? That review. All right, now I've got to be able to read it. You've got to show me your work. That's 25 points that cannot be dropped. If you need me, then send me an email and we can get together one-on-one, okay? So it'll probably be, maybe if you turn it on Wednesday, maybe I can get them to you by Monday, I hope so. But for sure by Wednesday. If you need help, come see me, okay? All right.